The Webb Space Telescope was December 25 last year. After 29 days of flight, it reached its destination Lagrangian point orbit and has been in orbit for 2 weeks today. Webb team members saw the first photons of starlight that traveled through the entire telescope and were detected by the near-infrared camera, NIRCam, instrument. This milestone marks the first of many steps to capture images that are at first unfocused and use them to slowly fine-tune the telescope. This is the very beginning of the process, but so far the initial results match expectations and simulations. To work together as a single mirror, the telescope's 18 primary mirror segments need to match each other to a fraction of a wavelength of light, approximately 50 nanometers. To put this in perspective, if the Webb primary mirror were the size of the United States, each segment would be the size of Texas, and the team would need to line the height of those Texas-size segments up with each other to an accuracy of about 1.5 inches. With deployment of the mirror segments now complete, and the instruments turned on, the team has begun the numerous steps required to prepare and calibrate the telescope to do its job. The telescope commissioning process will take much longer than previous space telescopes because Webb's primary mirror consists of 18 individual mirror segments that need to work together as a single high-precision optical surface. The steps in the commissioning process include segment image identification, segment alignment, image stacking, coarse phasing, fine phasing, telescope alignment over instrument fields of view. It iterates alignment for final correction. 1. Segment image identification. First, we need to align the telescope relative to the spacecraft. We are pointing the telescope at a bright, isolated star, HD 84406, to capture a series of images that are then stitched together to form a picture of that part of the sky. We'll actually capture 18 slightly shifted copies of the star, each one out of focus and uniquely distorted. We refer to these initial star copies as segment images. One by one, we will move the 18 mirror segments to determine which segment creates which segment image. After matching the mirror segments to their respective images, we can tilt the mirrors to bring all the images near a common point for further analysis. We call this arrangement an image array. 2. Segment alignment. We begin by defocusing the segment images by moving the secondary mirror slightly. Mathematical analysis, called phase retrieval, is applied to the defocused images to determine the precise positioning errors of the segments. Adjustments of the segments then result in 18 well-corrected telescopes. However, the segments still don't work together as a single mirror. 3. Image stacking. To put all of the light in a single place, each segment image must be stacked on top of one another. In the image stacking step, we move the individual segment images so that they fall precisely at the center of the field to produce one unified image. This process prepares the telescope for coarse phasing. The stacking is performed sequentially in 3 groups: I segments, B segments, and C segments. 4. Coarse phasing, then one big one. Coarse phasing measures and corrects the vertical displacement, piston difference, of the mirror segments. Using a technology known as dispersed fringe sensing, we use NIRCam to capture light spectra from 20 separate pairings of mirror segments. The spectrum will resemble a barber pole pattern with a slope, or angle, determined by the piston difference of the 2 segments in the pairing. Top indicates a large piston error or bottom indicates a small piston error. 5. Fine phasing. Fine phasing is conducted directly after each round of coarse phasing, and then routinely throughout Webb's lifespan. These operations measure and correct the remaining alignment errors using the same defocusing method applied during segment alignment. However, instead of using the secondary mirror, we use special optical elements inside the science instrument which introduce varying amounts of defocus for each image, -8, -4, +4, and +8 waves of defocus. A simulation of the defocused images used in fine phasing. The images, top, show defocus introduced to an almost aligned telescope. The analysis, bottom, indicates the errors associated with each telescope segment. Segments with very bright or dark colors need larger corrections. Credit, NASA. 6. Telescope alignment over instrument fields of view. After fine phasing, the telescope will be well aligned at one place in the NARCam field of view. Now we need to extend the alignment to the rest of the instruments. In this phase of the commissioning process, we make measurements at multiple locations, or field points, across each of the science instruments, as shown below. More variation in intensity indicates larger errors at that field point. An algorithm calculates the final corrections needed to achieve a well-aligned telescope across all science instruments. 7. It iterates alignment for final correction. After applying the field of view correction, the key thing left to address is the removal of any small, residual positioning errors in the primary mirror segments. We measure and make corrections using the fine phasing process. We will do a final check of the image quality across each of the science instruments. Once this is verified, the wavefront sensing and controls process will be complete. As we go through the 7 steps, we may find that we need to iterate earlier steps as well. The process is flexible and modular to allow for iteration. After roughly 3 months of aligning the telescope, we will be ready to proceed to commissioning the instruments.